Design and implementation of Z Source Resonant Converter for EV wireless charging application. Abstract Wireless Power Transfer, WPT, technology is an emerging research area due to its safety and convenience. A conventional WPT system has front-end PFC and DC-DC boost converter which makes the system bulkier. The Z Source Inverter, ZSI, was introduced into WPT systems to improve the system performance. The ZSI regulates the input voltage in WPT systems without front-end converters and makes the inverter bridge immune to shoot-through states. The results are through simulations and finally, the design system is implemented experimentally. Introduction. WPT technology deliver power through an electromagnetic field without any physical connection between the transmitter and receiver. 1-3. Recent advancements in this field have led to more stringent design requirements being proposed and studied by researchers, such as efficiency improvement 4-8, coupling variation 9, 10, foreign object detection 11, 12, and output regulation 13-15. Electronic technology plays a crucial role in these research studies and spurs WPT technology development. The voltage source inverter, VSI, is an essential part of a WPT system that generates high-frequency AC power for transmission across a wireless media. Unfortunately, the output voltage of conventional VSI is always equal to or lower than the input voltage, which limits this inverter's application in small voltage or wide input situations. To address this barrier, front-end converters, such as boost converter or buck boost converter, are inserted between a DC source and a VSI to boost the DC rail voltage 16, 17. However, this require more space and increase the cost of the system. To add one additional IGBT/MOSFET, one extra heatsink and associated drive circuitry is to be accommodated. Considering the incremental cost and design complications, the ZSI presents a better alternative to front-end converters in WPT system. When compared with a conventional VSI, the ZSI has an input diode DS and a Z source network added between the DC voltage source and the VSI 18. The Z source network consists of two identical inductors, L1 and L2, and capacitors, C1 and C2, to boost the output voltage by shorting one or two legs of the rear-end inverter bridge. This is also referred to as the shoot-through state. Guidelines to design Z-source network based on steady-state parameters were presented in 19. Since the network is connected to a three-phase VSI, the output current of the network is regarded as a constant current. Meanwhile, the current in the network of WPT system is approximately sinusoidal over part of one switching period due to a sinusoidal resonant current. The mathematical analysis in 19 is modified when applied to a WPT system. In 20, the benefits of a ZSI in resonant converters are analyzed. These benefits include improved robustness and reliability buck/boost function, and high efficiency over wide input and load ranges. The ZSN in the proposed ZSRI provides the unique feature of inherent power factor correction, PFC, without adding extra switching devices. It is possible because it adds the unique features of immunity to the H-bridge inverter during shoot-through states. This characteristic makes the input current as a sinusoidal waveform and in phase with the AC input voltage. This variable also provides a boost factor to the system. However, to regulate the output voltage, the proposed ZSN-based inverter uses the active state duty cycle, which is a common control variable used in series resonant inverters. Both control variables are used in the series resonant H-bridge inverter, and the ZSRI does not require additional control circuitry to provide power factor correction. In other words, because of the ZSN, the ZSRI can perform power factor correction as well as DC/AC conversion in single stage. 2. Operation of Z source resonant converter. The ZSRC has more states in one switching cycle compared with other DC-AC systems. It is important to clarify all these states to understand the ZSRC. The boost ratio of ZSN is still related to the total shoot-through state duty cycle among these states. The operation principle of the ZSRC is described based here with an example of the phase shift control method. Assuming that the ZSN is symmetrical, C1 equals C2 equals C, and L1 equals L2 equals L, therefore, VC1 equals VC2 equals VC, and VC1 equals VC2 equals VC. Also, the resonant frequency of L and C in ZSN is at least 10 times smaller than the switching frequency. Hence, the ZSN inductor current and the ZSN capacitor voltage are considered to be constant in one switching cycle. Fig 2 shows the conducting devices in different states: active state, shoot-through state, and zero state. Fig 1. Circuit of WPT system with a ZSI. 1. Active state. During the two active states time interval see Fig 6, C, and G, the diagonal switches array on, and the input side diode D1 is conducting. The resonant network draws current from both the ZSN inductor and capacitor. The difference between load current and ZSN inductor current is provided by a series connection of the two ZSN capacitor and source. The current going through the switches array only load current. The ZSN inductor voltage for this time interval is given as 2. Shoot-through state, 3 of the switches are on. The two horizontal switches are carrying the load current and the switches in one phase leg are carrying the ZSN inductor current. Hence, there is one switch carrying the sum of the two currents. Since the flow of ZSN inductor current is always in one direction and the load current would be bipolar, these two currents either subtract from each other or add together, contributing to the sum with their absolute value. Fortunately, phase shift control only allows different polarity currents going through the same switch in shoot-through state. Here, the ZSN capacitors will charge ZSN inductors. This is how ZSRC can boost the voltage. The ZSN inductor voltage for this time interval is given as 3.0 state. During the 0 states time interval, two horizontal switches are on. The ZSN is isolated from the load. The load current is freewheeling and the ZSN inductors charge the ZSN capacitors. The ZSN inductor's voltage for this time interval is given as. These three states are all the possible states in ZSRC. Different allocation of these three states along one switching period would generate different load regulation characteristic. Fig 3. Time domain waveforms for phase shift control in ZSRC. 3. Simulation of WPT system with ZSI. Simulation of Z Source Resonant Converter for EV wireless charging is done using MATLAB/Simulink 2016. 1. Simulation parameters. Simulation parameters are shown in Table 1. Table 1. The input voltage of the ZSRC is Vs equals 33V and the output voltage and current is VO equals 88V and IO equals 2.28A with the resonant frequency of 20 kHz. Assuming that the ZSN is symmetrical, C1 equals C2 equals C, and L1 equals L2 equals L, therefore, VC1 equals VC2 equals VC, and VL1 equals VL2 equals VL. Also, the resonant frequency of L and C in ZSN is at least 10 times smaller than the switching frequency. Hence, the ZSN inductor current and the ZSN capacitor voltage are constant in one switching cycle. The significant part of the design is choosing the inductor and capacitor values and operating frequency. On the contrary, use of the low frequency leads to increases both on the size and also the cost of inductors and capacitors. Thus, there is a trade-off between the size and efficiency in determining the operating frequency of the converter. The frequency is selected as 20 kHz. 2. Simulation result. The complete model of the developed WPT is shown in Fig. 4. Simulation has been performed and the results are presented for each converter stage. The circuit consists of a high-frequency, HF, Z-source resonant converter. High-frequency switching is implemented using MOSFET switches. This is the high-frequency link. A HF transformer provides voltage transformation and isolation between the DC source and the load. At the output side, a full bridge rectifier is connected to load. For analytical study, a resistive load is selected. The closed loop is controlled for constant output. 4. Hardware implementation. The main circuit diagram consists of 4 sections: converter section, control section, driver section, and power circuit. The converter section consists of 4 IRFP460 and MOSFETs. Even if there is any fluctuations in the input, the output will be maintained constant by the program stored in the microcontroller. Microcontroller sends the corresponding signals, which will be too feeble to drive the MOSFET switches, so a driver circuit consisting of TLP250 driver are used, which boosts the amplitude of the signals enough to drive the switches. Conclusion. A new circuit topology for high-power WPT applications using a full-bridge Z Source Resonant inverter has been developed and simulated. The control methods in the system with the insertion of shoot-through modes of the Z Source Inverter have been investigated. In simulation, ideal MOSFETs and diodes were used. The output voltage of 27 V and output current of 0.9 A, I.E output of 23.5 W is obtained for the coupling coefficient K of 0.2. In the experiment, an output current of 0.9 A, and output voltage of 16 V was obtained. The slight difference between the simulation and experimental results is due to the following reasons: core losses, simulation ideal diode, and MOSFET switches were used. Nevertheless, in both the simulation and experiment, the results obtained are very close to the analytical design value. This, in turn, validates the designed parameters.